In the winter of 1942, Germany's most advanced locomotives froze into useless statues. 70% were knocked out when oil turned to sludge and copper pipes shattered as temperatures plunged to -40 degrees Celsius. The whole Eastern Front began starving for fuel, food, and ammunition because beautifully engineered trains simply stalled in the cold. With disaster looming, Nazi planners did the unthinkable. They ordered engineers to gut their own designs, chop out 6,000 parts, and build trains from cheap steel with no insulation, all intended to last just 5 years. They built them to be disposable. Instead, these crude machines outlived the regime that created them, powering half of Europe for 5 decades. How did wartime desperation create an immortal machine? And why did the world's garbage train become unkillable when brilliance failed? Steel contracts and shrinks in the cold, but what really killed the German locomotives was not just the metal, it was what flowed inside. Lubricants designed for mild European winters thickened into sludge at -40 degrees Celsius. Grease in the bearings turned to a stiff paste. Pistons, meant to glide with a thin film of oil, scraped and seized. Every moving part that relied on smooth motion became a grinding, frozen obstacle. The most advanced component, the feed water heater, was supposed to make the engine efficient by pre-warming water before it hit the boiler. But in the Russian winter, these heaters became death traps for the locomotive. Water inside expanded as it froze, splitting copper tubes with a sharp crack. Once brittle, the copper shattered. Pipes meant to carry steam or water simply burst, spraying ice and metal shards across the machinery. Valve assemblies built with tight tolerances for maximum power jammed solid. The intricate copper piping that wound through the engine became a network of fracture points. Each break meant more than a repair. It meant a dead engine stranded miles from help. Even the boiler drains, designed to clear out water, clogged with ice. Crews swung hammers to break loose valves or tried to thaw lines with torches, but the cold always won. By the time the sun rose, hundreds of locomotives stood silent and useless, their wheels locked and their boilers split open. The precision that had powered Germany's railways now left them helpless. The Eastern Front's winter exposed every weakness in the design, not through sabotage or enemy action, but through the simple, relentless mechanics of cold. The result, a fleet built for efficiency, was paralyzed by the very features that once made it superior. Supply lines stretched from Berlin to the edge of Stalingrad, but the rails themselves became a graveyard. With 70% of the locomotive fleet frozen solid, the backbone of the German advance snapped. Freight cars packed with rations, ammunition, and winter uniforms stood abandoned, locked behind silent engines on tracks buried in snow. The army at the front waited for trains that would never arrive. Every stalled locomotive meant another division left hungry, another artillery battery short of shells, another hospital tent running out of bandages. The entire war effort depended on a river of steel and coal that had simply frozen in place. The Wehrmacht's supply doctrine relied on those trains. Trucks could not cross the endless mud and ice of the Russian steppe, and horse-drawn wagons collapsed under the weight of modern warfare. Only rail could move the thousands of tons needed each day to keep the front alive. But with most of the engines crippled, the daily tonnage dropped by half or more. Divisions began to run out of fuel and food. Artillery shells piled up in depots hundreds of miles from where they were needed. Reinforcements and wounded men alike found themselves stranded, unable to move forward or retreat. Railway officials logged the numbers in grim columns. Out of every 10 locomotives, only 3 could be coaxed into motion. The rest were frozen beyond repair or needed parts that no one could deliver. By December, entire sectors of the front were isolated. The German army, famous for its rapid movement, was now trapped by its own technology. The failure of the trains was not just a technical setback, it was a strategic collapse. The war on the Eastern Front was being lost not in the trenches, but in the rail yards and frozen sidings stretching from Smolensk to Rostov. Albert Speer's order landed on the desks of every locomotive engineer in Germany. Cut the labor, cut the steel, cut the time. The numbers were brutal. The peacetime BR-50 needed around 6,000 hours of skilled work to build, precision machining, careful fitting, copper pipes bent by hand, every valve seated tight. Wartime did not have that luxury. With the BR-52, the stopwatch and the scale became the only blueprints that mattered. Assembly time dropped by nearly 40%. Where one locomotive once ate up 6,000 hours, the new design rolled out in as little as 3,600 to 4,000 hours. That meant more engines, faster, with less skilled labor. Numbers mattered. Material savings were just as aggressive. The BR-52 shed 26 tons of steel per engine compared to its predecessor. That is the weight of a loaded freight car stripped out of every locomotive. Copper, once prized for its reliability, was simply too expensive and too scarce. Brass bushings vanished, replaced by rough steel. Feed water heaters, complex, copper-laced and freeze-prone, were deleted entirely. Even the connecting rods, once machined to a shine, were now cut from crude I-beams, left rough and unfinished. Drill presses gave way to oxyacetylene torches. If a hole needed to be made, it was burned in. If a part could be left out, it was. The parts count told the real story. Compared to the BR-50, the BR-52 slashed 6,000 individual components from its design. Each missing piece meant one less place for ice to form, one less thing to fail, one less spare to stockpile. Fewer parts also meant faster repairs and less to go wrong in the field. The factories scattered from Vienna to Breslau became production lines for a new kind of locomotive, not elegant, but efficient in the only way that mattered. Every shortcut was a gamble, but the alternative was paralysis. Parts were strategy. This was industry as a survival mechanism. The goal was not beauty or longevity. The goal was to get a working locomotive out the door using whatever materials and labor could be scraped together. In a war where every ton of steel and every hour counted, the BR-52 was engineered for the numbers, not the eye. Every shortcut taken in the BR-52's design left a scar in the metal, but some of those scars became its greatest strengths. The frost shield was not a single piece of armor, but a set of cold-blooded decisions that let the engine survive where others died. Instead of letting pipes run exposed along the frame, where they froze solid, the designers tucked them under the boiler jacket. There, waste heat from the firebox kept water and steam moving, even as the outside air dropped to -40. The pipework looked rough, welded in hasty lines, but it stayed warm enough to avoid bursting. Drains and sumps, once narrow and easily clogged, were simply enlarged. The logic was brutal. A bigger hole is harder to freeze shut. Crews could pull plugs or open valves, and the ice would break free, not choke the system. The drains were not pretty, but they worked, no matter how much slush or frozen mud tried to stop them. Chimneys got makeshift covers, not for style, but to keep snow from packing inside and to trap a little more heat. Even the cab, never designed for comfort, gained partial walls and crude windbreaks. It did not keep out the cold, but it gave the crew a fighting chance against the wind. The tender, though, was the real icon of wartime pragmatism. The Wannentender, the bathtub tender, looked like a half-finished oil tank welded to a set of wheels. Traditional tenders used complex frames and dozens of braces to hold their shape. The Wannentender was a single rolled steel shell, a unibody design that needed no internal skeleton. Water sloshed in a deep open tank, held together by the strength of the curved metal. This saved tons of steel and weeks of labor. The tank held up to 30,000 liters of water, enough for long runs across the steppe, and the coal bunker was welded right on top. There were drawbacks: the tub flexed on rough track, weld seams sometimes leaked, and the water could shift dangerously at speed, but the savings were worth it. Every one of these features was ugly, obvious, and effective. The frost shield suite in the bathtub tender did not just keep the locomotive running, they kept the war moving mile after frozen mile. In the language of logistics, beauty is measured in tonnage delivered, not in polished brass. The BR-52 was proof that a machine could be both disposable and unstoppable, so long as it was built to survive the worst the world could throw at it. Production of the BR-52 was not the work of a single plant or even a single country. Dozens of factories across Germany and occupied Europe were pressed into service. Vienna, Breslau, Berlin, and cities deep in Poland all churned out engines on a relentless schedule. The goal was simple: numbers mattered. Over 6,700 locomotives poured out between 1942 and 1945, a figure unmatched by any European steam design before or since. This swarm was a direct answer to Allied bombing. When one factory went dark, another kept the line moving. Components were standardized, so a boiler built in Austria could be bolted onto a frame welded in Silesia, then matched with a Wannentender from a plant in the Ruhr. Assembly lines ran day and night, with parts shuffled by rail between bomb craters and blackout curtains. Redundancy was built into every stage. If a shipment of steel was lost, another plant could substitute with whatever metal was on hand. Labor shortages were filled with conscripted and forced workers from across the continent. Each factory became a node in a vast, decentralized network designed to outlast air raids and supply chaos. The result was a locomotive that was never truly rare. On the rails of Eastern Europe, the BR-52 became as common as mud and just as hard to get rid of. This was not just mass production, it was industrial dispersal, a logistical answer to a continent at war. The sheer volume ensured that, no matter how many were lost, the trains kept coming. On the rails, the BR-52 was not just a stopgap. It was a brute force answer to a problem that had broken the best machines Germany could build. With a 210 zero-wheel arrangement and a low 15-ton axle load, it could roll over tracks torn up by frost heaves, artillery, or sabotage. Bomb craters and warped rails that would have sidelined heavier, more delicate engines barely slowed it down. The numbers tell the story. This so-called disposable locomotive could haul 1,200 tons of freight at 65 kilometers per hour on level ground. That is a line of boxcars stretching nearly a kilometer, moving fast enough to keep armies supplied and retreating columns out of reach. The loose tolerances that looked like shoddy workmanship on the assembly line became an advantage in the field. Bearings that rattled in summer did not seize in winter. If a rod cracked or a bearing box ran dry, a hammer and a few hours could get the train moving again. The rough steel bushings and torch-cut holes meant nothing needed to be perfect, just functional. Crews learned to trust the engine's stubbornness. It burned coal like a furnace, but it kept moving when everything else gave up. Even as the war ground on and the tracks fell into worse shape, the BR-52 just shrugged off the punishment. Its light axle load let it cross bridges that would have collapsed under older engines. It could snake through temporary sidings and haul heavy loads over makeshift repairs. The design was ugly, but it delivered what mattered: tonnage on time to the front. When the war ended, thousands of these so-called disposable locomotives were left scattered across a shattered continent. For the new governments in Poland, Austria, the Soviet Union, and Turkey, the logic was simple: rebuild with what was on hand. The Polish state railways took in hundreds of these engines and reclassified them as TI-2. Soviet railways absorbed them as the TE class. Turkish railways and the Austrian Federal Railways pressed them into service under their own banners. These machines, designed for 5 winters at most, became the backbone of post-war freight. In Poland, TI-2s hauled coal from Silesian mines to Gdansk for nearly half a century. Soviet TE locomotives pulled trains across the steppe well into the 1980s. Turkish crews ran them through the mountains until the end of the Cold War. Even Austria, with all its industrial pride, kept the stripped-down engines running until 1976. The reason was always the same. They were cheap to fix, easy to run, and impossible to kill. In the harsh economy of post-war Europe, a train that just kept moving was worth more than any promise of modernity. Long after the last shots of the war, the so-called disposable locomotives were still being counted. In East Germany, railway planners kept hundreds of BR-52s in sealed storage, ready to be fired up at a moment's notice. The reasoning was blunt. In a world bristling with nuclear weapons, diesel and electric trains could be wiped out by a single electromagnetic pulse. But a steam engine, built of crude steel and running on coal, was immune to blackouts and fried circuits. Even as the 1980s rolled in, with computers humming and electrified lines stretching across Europe, these wartime relics waited in the shadows. Their presence was a silent insurance policy, a mechanical safety net for a future that could collapse overnight. The logic was hard to argue with. Coal was cheap, and the BR-52 could be coaxed back to life with little more than oil, water, and a crew who knew their way around a firebox. When the Berlin Wall fell, some of these mothballed engines were still ready to roll, outlasting the regime that had stored them. Today, a handful survive in museums, sparking debate over what should be preserved: the high-tech marvels that failed when pushed to the limit, or the ugly, battered machines that just would not die. The question lingers: when everything else stops, what do you really want in reserve? Today, as industries chase ever greater complexity, the legacy of the Kriegslok endures. When resources run thin and systems fail, brute simplicity outlasts every plan. In an age of fragile supply chains and planned obsolescence, the most disposable designs can become tomorrow's backbone. Durability isn't always intentional, and in a crisis, it becomes everything. What do you think survives when technology breaks down? Drop your thoughts below.